The very last thing that we were doing in Stat 100 was hypothesis testing. And so far we've done 2 tests. The first one was the one sample Z test, and then the second one was the T test. So that Thursday before break, we went over the T test, and it's really similar to the Z test. The only difference is we use it when these 3 conditions are met. So just a really, really quick review about the T test. You only want to do it when you have a small sample size. Your data follows the normal curve, and then the SD of the population is unknown. So the T-test is for small samples. Basically, the deal is that if you don't know the SD of the population, you have to estimate it with the SD of the sample. And if you have a small sample, that can be a little bit problematic. We need to make an adjustment to that small sample SD. So that was the deal with the T-test. It's an adjustment for small samples. So the homework actually that you guys will be doing that's due tomorrow is all about when do you use Z versus T. So the easiest way to think about it is just double check if all of these conditions are met. And if so, you use T. So that was the last thing that we did. We did a couple examples. Remember, the T distribution is a little bit different than the normal distribution. Actually, on the first page, oops, I skipped this, but on the first page, it shows how the T distribution compares to the normal distribution. And the normal distribution is just the regular normal curve. It's the one that I highlighted, the one with the tallest peak. And then the T curves actually change depending on the sample size. So if you have a smaller sample size, the T curves have fatter tails. And then the bigger your sample size, the closer the T distribution is to the normal distribution. So that was what the T distribution looked like. And because the T curves change depending on the sample size, we have a slightly different T table than the normal table, because I didn't want to give you guys 25 T tables. That would be a little much. So we combined all of the T tables into one. So T distribution, we said it changes depending on the sample size, and it's defined in terms of degrees of freedom, which is really just the sample size minus 1. So it's n minus 1, but really, all you guys need to know is that it changes depending on the sample size. They do n minus 1 for a variety of reasons, but I think the one that makes the most sense is just that you have to have at least 2 people, right, in your sample. So that's why we start with 1 degree of freedom. And then all we do is, once we have our degrees of freedom, which I guess this problem, whatever problem this was, there were 15 degrees of freedom and T was 1.61. So you calculate T, just like Z, you find your degrees of freedom, and then to use the table, you basically go down to 15 and over to 1.61. But you probably won't find your exact T, but that's okay. You can find 2 that are in between yours, or that yours is in between, and then your p-value is going to be up here. So I said, okay, 15 degrees of freedom, T is 1.61, that's between 1.34 and 1.75, and then my p-value is going to be between 5 and 10%, which all I really care about is it less than 5 or not? So we said P is not less than 5 because it's between 5 and 10%. So that was the big thing about the T-test is the table is a little bit different. It's for small samples, and I think that was it. So more practice with that will come on the homework. But actually today, so let's see. I think I have 3, we have 3 chapters left. 22, 23, 24. And 3 hypothesis tests left. So I think what we're going to do is do 1 on each day of class. So like today we're going to do the 2 sample Z test, and then on Thursday we're going to do our next test, and then the last day of class we'll do the last test ever. So that's the plan. Luckily today should not be very bad. Should not be that bad because the 2 sample Z test is really similar to the 1 sample Z test. So 2 sample Z is super common because a lot of times we have 2 things we want to compare. Very common. right? Maybe we want to look at a treatment and control group, or males versus females, or I don't know, any two groups. And the one sample z-test doesn't really make sense because we only have one of everything. We just have one sample. We're not comparing it to another sample. We're comparing it just to a population. So with the one sample z-test, here was our test statistic, which is z. Test statistic, that's what we called the statistic we calculate for our test. So like for the t-test, it was t. And this was just, I always like to write it as value minus expected value over standard error. So observed is just the observed value. So that's the one sample z-test. We did that, right, back in the day. We did that. And now for the two sample z-test, you'll see the formula is basically the same. There's just two of everything. So our test statistic is still z because we're still doing a z-test. But now we have two observed values, two expected values, and then two standard errors. So we just have to combine those into one single test statistic. Let's see, it says if our null hypothesis is that the two population averages or percents are equal, the expected difference is 0. So a lot of times you'll see the z statistic for the two sample z-test as just the difference over the standard error for the difference, because this expected difference is always 0. Because we're trying to test, is there a real difference or not? There is a two sample t-test as well, but we don't have that in the book because it's basically just the same thing as the t-test. You're just going to make the same adjustments that we do for the two sample z-test. So, okay, so the observed difference is just going to be the two differences. And then the standard error for the difference, how do you compute it? It's actually not too bad. So we have two standard errors, two populations, and we want to combine them into one. So for the two sample z-test, our null hypothesis is always going to be the same. So it's always going to be that the population averages are equal, right? Because the null is it's the dull, boring one, the hypothesis of no effect. There's no difference. There's nothing weird going on. The two groups are the same. And that's where this comes from. The expected difference is always going to be 0. And so we're going to have actually two, and then the alternative is going to be that they're not equal, right? Or that one group is higher than the other or lower than the other. So for our test statistic, let's see, z, I'm going to take my observed difference minus my expected difference, which is 0, divided by the standard error for the difference. And the way we're going to calculate it is like this. So it's unfortunately, you can't just subtract the two standard errors. That has to do with the square rooting in the formula for standard errors. So instead, we have to square them first, add them together, then take the square root. So this is kind of like, this formula actually comes from the Pythagorean theorem. Like if you have a right triangle, A, B, and C, A squared plus B squared equals C squared. If you remember that from high school, it's the same thing. It's like standard error 1, standard error 2. And if we wanted the standard error for the difference, if we wanted to combine the two, we have to take the square root. So that's where it comes from. We'll do an example so you guys can see what this is like. But this formula, I feel like is not super intuitive because you might think, can't you just subtract them? But again, it's those square roots that make it so that you have to square them first. If any of you have heard of variance is just the standard error squared. Variances are easier to work with because you can just add and subtract them, but they're not as intuitive. So anyway, that's how you find it. It does say the formula doesn't work if the two samples are dependent, but that isn't super relevant for us because we're not going to do any examples where that is the case. That's usually not the case, but disclaimer, so we decide to put it in the book. Okay, let's do our first example. So back to hypothesis testing. This will be a good review from over break. When we first did our very first one sample z-test, we did our test in 5 steps, and that actually works for every single hypothesis test. So here, I can do those same 5 steps. I am going to right away say, all right, they're telling me I'm dealing with averages, and I know this is going to be a 2-sample z-test, because if I read this, we're comparing 2 different groups of people. So the 2-sample z-test is really easy to recognize because there's going to be 2 of everything. So let's see. This was a study back in 2003. They were comparing the results of a low-carb diet, the Atkins diet. I don't know if you guys... I guess you were alive during this time, but you might not remember this. The Atkins diet it's your traditional low carb diet, and people were doing it and they were losing a lot of weight. They were saying it's an amazing diet. It helps you lose weight and it helps you do it quickly. So they wanted to test, does the Atkins diet work better than just a traditional like counting calories diet, low calorie diet? And so there were some skeptics. They were like, why should we do this Atkins diet? Is it even worth it for losing weight? So they did a test. And I guess before we get into this, the Atkins diet was kind of weird because it told the people that you can eat as much meat as you want. So that's why people were skeptical. They're like, as much of something as you want? How does that help you lose weight? So you can eat as much meat as you want, was the Atkins diet. And so they thought, okay, what better to do than a hypothesis test to test, does this diet really work? So it says the subjects were 63 obese men and women. They randomly assigned 33 of them to the Atkins diet and 30 to a traditional low-calorie diet. And these people were chosen from a population of thousands wanting to lose weight. So they had them do this diet for 3 months, and the results were pretty good. Let's see. It says after 3 months, the Atkins group lost an average of 6.8% of their body weight. So that was their average weight loss percent. The SD was 5%, and then the other group lost 2.7% of their body weight. And their SD was 3.7. So there's 2 averages, 2 SDs, and 2 groups of people. So that's how I know this one's the 2-sample z-test. So I think that's a question, whenever we do these hypothesis tests, students ask me, like, how do you know which one to use? And this one, you'll always know. There's 2 of everything. So the question is, could this difference be due to chance, or did the Atkins diet really work better? So 6.8 versus 2.7, is that difference big or not? So we can do a test to figure that out. So step 1 is always to state my null hypothesis. Okay. And for the 2-sample z-test, it's always going to be the same. On the other page, I think I wrote it down. Yes, I said it's the 2 averages are equal. The null is that there's no difference between the 2 diets. So I'm going to put, let's see, I can write this a bunch of different ways, but I think I'm going to say the average weight loss percent in the Atkins population is equal to the average weight loss percent in the low-calorie population. So, sure, in our sample, we got that they were slightly different, but the null is saying that difference is just due to chance. The true averages are equal. So we're going to decide at the end, what's the probability we get that difference if there really is no difference? What's the probability we get that difference by chance? So this is always going to be your null hypothesis. And on the final, there's going to be a question. I'm going to ask you guys, what is the null hypothesis for the two-sample z-test? And this is probably one of the most commonly missed questions. People will say, oh, that the Atkins group is 6.8 and the other group is 2.7. Well, that's what we got in our sample, but our null is the boring one that says they're always equal. So just remember that. Null is dull. Then you can't go wrong. The alternative is saying, okay, we found evidence in our sample that the Atkins diet works better. So I'm going to say the Atkins. So this average is bigger than the other average. Average in Atkins is greater than the average in the low-calorie one. Or I could just say the Atkins diet works better for weight loss. That's what people were arguing, so that's what we're trying to test. And we did see evidence of that in our sample. All right, step one, done. So nothing too new so far. Step two is to draw, I always say, draw your null box. But for the two-sample z-test, we actually have two boxes. We have two null boxes. Okay, because we have two samples. And we want to, for the null box, you always want to assume the null is true. So we're going to assume that our two populations, so we have thousands of people who are on the Atkins diet, thousands of people who are on a traditional low-calorie diet, and we're going to assume for the null that the averages are the same. I guess what I was saying, commonly missed questions, it's this one. It's the one that says, describe the boxes. That's where people say, I guess they kind of go hand in hand. People are like, oh, this one has an average of 6.8. This one has an average of 2.7. Well, if it's the null box, that's the whole population. So we're saying, we're assuming the null until the very end of the test, if there's evidence otherwise. So I'm assuming the averages are the same. If I draw, so taking our sample is like drawing 33 times for the Atkins group. Draw 33 times and then 30 times, right? Yeah, 30 and 33. And find their average. And so we got an average of 6.8% for the Atkins diet and an average of 2.7% for the low calorie. So we expected to get the same average, but we got different averages. So the question is that difference due to chance or not? So the only difference so far is that we have two groups, two of everything. Two sample sizes, two averages, and I could even say, I guess if I wanted to, the two SDs as well. Okay, so our probability model is saying we have these populations, we're randomly picking people out of them, calculating statistics, and we got a difference, and we expected not to. So our very first iClicker question is going to be hopefully an easy one. It's just going to be, I guess I didn't say, it's going to be, do we draw with or without replacement? Which at this point, hopefully you guys are all good. A is with, B is without. Oops, there we go. So I'll let you guys answer. Hopefully everyone gets it right, and then we'll move on. All right, this looks good. I think most of you guys have responded. And let's see. Yay, 91% of people said without. That looks good because we don't want to sample the same person twice, right? Anytime we do surveys, we want to do it without replacement. Okay, perfect. I'm going to add that. 33 times without replacement, and then also 30 times without replacement. Because you don't want the same person's data to be in your survey twice. Okay, so that's our scenario. So our next step is to calculate our test statistics. So we want to know how far is 68 from 2.7 in terms of a z-score. And so this is the two-sample z-test, so I'm going to use z. So z is your observed values, your difference in your observed values minus your expected values over the standard error for the difference. So let's see, that's the observed difference minus the expected difference over the standard error for the difference. So my observed difference is just what I got, 6.8 minus 2.7. So it's the difference between your two values in the two groups. The expected difference is always 0. I expected no difference. And then I got to find my standard error for the difference. You might be wondering, does it matter? I did 6.8 minus 2.7. Does it actually matter which order you do that in? And the answer is no, it doesn't matter. So even if I did 2.7 minus 6.8, I'd get the opposite sign for my z-score, which would be okay. I'd still have the same p-value. So you'll notice I always like to do it so that you get a positive z-score, but it really does not matter which way you do it. Okay, so that formula was basically to take the standard error for the Atkins diet and square it, plus the standard error for the low-calorie diet and square it. So that's from the other page. And I don't have the standard errors, but I can calculate them really quickly. Let's see, so for the Atkins diet, my standard error is going to be... here I'm dealing with averages, right? So my standard error for the average is just the standard deviation over the square root of n. It's the standard deviation of the box or the whole population. But we don't know the standard deviation of the whole population, but we do know what we got in our samples. And our sample sizes are big enough. They're bigger than 25. We don't need to worry about using the SD plus or anything like that or doing a t-test. So I can just plug in for the Atkins diet. My SD was 5 and N was 33. And then for the low-calorie diet, my standard error was 3.7 and my N was 30. And let's see, what are those? This one is 0.87, and then this one is 0.68. So this I guess is kind of a weird example because we're dealing with percents, but it's average percent. So I don't want to, I'm just going to leave it like that. This is a strange one. We won't have any other examples like this, but it's average percent. Because if we just looked at average, like the number of pounds people lost, it would be biased because people started off at different weights. So that looks good. So basically what I would do is plug in 0.87. 0.87 squared plus 0.68 squared. So I'd add those together and then take the square root. So just make sure when you're doing this in your calculator that you put the whole thing under the square root. And that gives me 1.1. So let's see, 6.8 minus 2.7 over 1.1. So my z-score is 3.7. That's z, that's my test statistic. So that is going to help me find my p-value. What's the probability I get this difference if I'm drawing from populations with the same average? So step 4 is to find my p-value. And this is just a z-test. So the p-value we find exactly the same way as we did before. So I don't have to use the t-table. I don't have to use degrees of freedom. It's just a regular z-test. So here is, let's see, here's 0, here's 1, here's 2, here's 3, there's 4. So 3.7 is about right there. That's my z-score. So this is seeing my difference technically. So this is the 6.8 minus 2.7. This would be a difference of 0. So now it's a little different because we don't have one number, we have 2. But this is my difference. This is the expected difference. And then the p-value is just the probability I get my difference or an even bigger difference by chance. So the p-value is always going to be the tail. And the way I figure this out is just if I look up 3.7, that will give me the middle area between positive 3.7 and negative 3.7, which let's look at that really quick. Our p-value, I think, is going to be tiny, but we definitely want to use the normal table to figure out the exact amount. So here it is. Here's my normal table. Here's 3.7. The middle area is 99.978. So if I go back here, 99.978%. And then to actually find my p-value, that's the tail, so that's going to be a really small number, 100 minus 99.978 divided by 2, and it gives me 0.011%. So less than 0.1%, I guess. A little more than 0.01%. So that's my p-value. And then the conclusion, I'm going to put up 2 options for the conclusion. I want you guys to pick the best one. So the last step of the test is to say, okay, so what's the deal? Does the Atkins diet work or not? So here are the 2 options. There it is. All right. So I want you guys to pick, oops, there's 3. I thought there were 2. There's 3 actually. So pick the best one out of these 3. All right. Okay, I'm going to stop and see what you guys said. Okay, most people said A. What was A? We can conclude there's evidence that the Atkins diet works better for weight loss. All right, let's check. I think that sounds good. So our p-value it's a probability, right? And it's the probability that we'd get our difference, or a bigger one by chance. So if there's really no difference, it's the probability we get our difference or a bigger one just by chance. So that probability is super low, right? So our conclusion, we're going to say our p-value is less than 5. It is 5 or below. So that means we're going to reject the null. So it looks like you guys are actually absolutely right because we're rejecting this. The averages probably aren't equal. There's evidence the Atkins diet does work better. So I'm going to say p is less than 5, so we reject the null and conclude there is evidence that the Atkins diet works better. Okay. So that's what they found. There was evidence, at least after 3 months. Disclaimer, low-carb diets actually, when they did a bunch of other studies, and when you look at them over a long period of time, like over a year, they're actually very similar to the low-calorie diets. But for 3 months, like if you want to lose weight quickly, this seems to be the way to go, I guess. It was significantly different. So that was that. That was a good example.